So now let's talk about using lenses with our geometric optics. We're going to start real quick with refraction, and we'll start with that nice flat plane interface where the light hits a flat surface. We previously talked a little bit about refraction, and we're going to add in the piece of apparent depth. So when you look down into the water at an object, the object is in a different place than it appears because the light has bent. And there's a mathematical expression based on Snell's law that tells us where we can find the image versus where we see the image. And it's the image height is equal to the ratio of the two indexes of refraction times the object height. So not all surfaces are nice and flat. So we're going to be talking a little bit about those curved surfaces, the convex one and the concave ones. In the picture below, you see a convex surface, and we're not quite to thin lenses yet. So this is just a curved surface at an interface between two different indexes of refraction. And the image below is showing the going from an optically less dense material to an optically more dense material. It also shows that there's an object at the focal point, which they're calling the first focus. And once the light goes from that focal point through the interface, it goes off to infinity. So there is really no image. A couple equations to deal with this, also based on Snell's law. You just have to keep all of these subscripts straight. Label your drawings 1 and 2. Keep things very, very straight. Our second case is going to be the convex surface. So in this case, the focal point is inside the curve, and the light is going into the surface parallel to the axis from infinity, and then it's going to focus inside the new material at what's called the second focus. Once again, got to keep track of all of those subscripts. So there are a few rules for keeping track of these things. And for convex and concave surfaces, they're mathematically very similar. So if the radius is positive, then the surface is convex towards the object, which is what's shown in this picture. Otherwise, it's negative. So concave would be negative. And then the image distance is positive if the image is real and on the opposite side from the object. Otherwise, the image distance is negative. So now we move away from the interface with two different materials to basically a double refraction, which would be the thin lenses. The light's going to go in and bend, it's going to bend again, and we approximate it by saying it's going to bend once at the center of the lens. Two different types of lenses, although there's multiple different varieties of each kind. You have converging lenses, where all the rays come in parallel and are bent to a single focal point on the opposite side of the lens. And then you have diverging lenses where the light comes in parallel to the optical axis and it actually bends away from the optical axis, and the focal point is going to be on the same side of the lens as the object. So let's start by looking at the lens tracing for the converging lenses. And this is very similar to the spherical mirrors. There are rules for all these. Use a straight edge to keep things lined up nicely to find your image if those things are going to matter for you. First ray starts at the top of the object, it goes to the lens, and it bends at the center of the lens through the focal point on the other side. And then our second ray goes right through the center of the lens and just keeps on going. And then our third ray is kind of backwards of the first. It's going to go through the focal point on the same side as the object, hit the lens, and then run parallel to the axis. And where those lines intersect, you're going to draw the image. And in this case, we mapped the top of the arrow, so we're going to put the top of the arrow where the lines intersect. and the bottom of our arrow is on the axis, so that gives us our image. And if you look at the illustration, this is a real image. It's inverted. It is also smaller. The diverging lens is a little bit more complicated because you're going to have to backtrack some of the rays in kind of an imaginary sense. The rays don't really go this way, but this is where the image is going to appear, because you're not going to get an image on the other side of this lens because all of the rays move away from each other. So when you take that first ray, it's going to be just like the converging lens. It's going to head straight to the lens, parallel to the optical axis, but it's going to bend away once it goes through that lens. So you're going to use your imaginary line and continue it through the focal point on the same side as the object. The second ray is going to go through the center of the lens, and then the third ray is going to go to the lens as if it was going to go to the focal point, but once it hits the lens, it's going to go parallel to the axis, and so you're going to backtrack that parallel piece, and where those lines intersect, you're going to draw your image. And in this case, the image is a virtual image. It's upright. It is on the same side of the lens as the object, and this is not going to be able to be projected anywhere. Couple equations for thin lenses. You've got 1 over the object distance plus 1 over the image distance is 1 over the focal length. Or you can rewrite this equation to completely rely on the indexes of refraction and the radiuses of curvature. And this is helpful if you're actually dealing with eyeglasses, because you don't have to deal with the image and object distances. And then the magnification equation is going to be the height of the image over the height of the object is equal to the ratio of the image and object distances. Very similar to our mirrors. And just some final rules to help keep things straight. Image distance is positive if the image is on the opposite sides of the lens from the object. So that's going to be your real image. And it's negative if both the image and the object are on the same side. The focal length is positive for a converging lens and negative for a diverging lens, kind of related to that opposite sides and same sides idea. And then along those same lines, you've got a positive radius of curvature if the convex surface faces the object, and it's negative if the concave surface faces the object. Lots of little things to remember. Diagrams are going to be really helpful solving these problems, even though the math is really nice and straightforward. All right, good luck.